In part 3 of the algebra of functions, we're going to look at the difference quotient of functions, and we're also going to look at composing functions with one another. And so let's get started. The expression f of x plus h minus f of x all divided by h is called the difference quotient. This has applications in calculus when determining derivatives. It is considered the measure of the average rate of change of the function over an interval. That interval is the length of h. And the limit of the difference quotient is the instantaneous rate of change, and that's what we call the derivative of a function. And so in a college algebra, as one of the prereqs for calculus, we practice evaluating the difference quotient without looking at the limit of the difference quotient. So that's what we're going to look at right now. The process for doing this, I like to do it piece by piece. They're going to tell us the function we're performing the difference quotient on. In this case, for this first example, we have f of x equals 5x minus 2. So we already have this part of the difference quotient. We want to make sure we find the f of x plus h. So remember, f of x plus h is just where we replace the x's with x plus h. So that would be like this, and then we would distribute the 5 and simplify and combine like terms. So then we would have the second piece, and then we subtract those from one another and divide by h. So we already have the f of x. We're finding the f of x plus h. So let me finish that part. So this would be 5x plus 5h, because this distributes to both terms inside the parentheses, minus 2. Okay, we can't combine any like terms, so that is what f of x plus h is equal to. So now I'm going to plug in each part into the difference quotient. So I start with f of x plus h, which is 5x plus 5h minus 2. I subtract my f of x, put that in parentheses because the subtraction is for the whole function, not just one part of it. Okay, and then this whole thing is all over h. Let me make that clearer as an h. So I'm going to kind of color code up here each part. The purple here is my f of x plus h minus my f of x, which is right here, all over h, which I have right here. So now what I can do is I can simplify this difference quotient. I can distribute the negation here to both terms in the numerator. So I end up having 5x plus 5h minus 2 minus 5x plus 2, because negative times positive 5x equals minus 5x, and minus times negative 2, or you can think of this as a minus 1, ghost 1. I'm going to draw a little dotted 1 there. Negative 1 times negative 2 is a positive 2, and then all over h still. Okay, and so then notice what happens. 5x minus 5x, those cancel. 5x minus 5x is equal to 0. They cancel out. Minus 2 plus 2 cancels. That's equal to 0. So all we're left with is 5h divided by h. H divided by h is equal to 1. So this just equals 5. So the difference quotient for this function is equal to 5. Let's do the next one. Again, I'm going to color code. Let's color code. We have purple. So f of x plus h will equal x plus h squared minus 3x plus h plus 8. So I'm going to have to multiply this out, expand it out, and then simplify everything down. The f of x is already given to us right here. So we'll find those two parts, substitute that into the difference quotient, and then simplify as much as we can. So let me finish expanding out the f of x plus h. X plus h squared is going to be equal to x squared plus 2xh plus h squared. Then minus 3 distributes to both terms here. So I have minus 3x minus 3h plus 8. Okay, so that is equal to my f of x plus h. So we're going to take that, then we're going to subtract the f of x from that and have it all over h. So let me write it color-coded. Then before I do that, is there anything that cancels or can combine? No, because this is an h or x squared. This has an xh. This is h squared, x, h, 8. Nothing combines. There's no way I can simplify that, unfortunately. So let's write it out. X squared. So I'm going to write dq for my difference quotient. X squared plus 2xh plus h squared minus 3x minus 3h plus 8 minus, in green, x squared minus 3x plus 8, because that's our f of x. All of this over h. Woo! We're not playing today. This is a complicated one. Now I'm going to distribute the negation, or the -1, the assumed -1, to here. So I end up having x squared minus 2xh plus h squared minus 3x minus 3h plus 8 minus x squared plus 3x minus 8 all over h. I'm going to keep my colors the same. Now I can combine like terms. X squared minus x squared cancels to 0. Minus 3x plus 3x cancels to 0. Plus 8 minus 8 cancels to 0, because 8 minus 8 is 0. So what we're left with is, and I'm going to rearrange it so that the h squared is first, h squared minus 2xh minus 3h all divided by h. Now in the numerator, I can factor out an h. Let me keep that orange here. In the numerator, I can factor out an h. So I end up with h times h minus 2x minus 3 all over h. Since I was able to pull out an h and I have an h in the numerator and an h in the denominator, those can cancel because h divided by h is 1. And then, so that ends up simplifying all the way down to h minus 2x minus 3. So that tells us our difference quotient, which is our average rate of change over the interval h. H could be any number ever. It could be any real number. Okay? So these are two examples of applying the difference quotient. The last part of this section is going to look at composing and decomposing functions. The composition of f and g, denoted f, little o, g, it kind of looks like it's saying fog, but we say it as f of g, is defined of f of g of x equals f evaluating at g of x, which essentially means in kind of layman's terms, plug function g into function f. Okay. I know that sounds insane. We're going to see examples. We can also compose the other way around, and we can do g of f of x, which is plugging function f into function g. Sometimes you'll see it represented this way. Sometimes you'll see it represented this way. My preferred way is this way. I think it makes more sense because you're plugging in the g of x into the f of x, and I don't get confused by the order. But you could possibly see that both ways. Okay, same thing here. You might see it as g o f of x or g evaluating at f of x. So what that literally is saying, though, is that I'm going to take my function of g and plug it in for the x values in my f of x. Let's see an example and see how this works. So f of g of x is going to be, I have my x squared minus 3 times x plus 1. Okay, so what I am plugging in for my x values for my f of x is my g of x, which is 5x plus 4. So I'm going to do 5x plus 4, 5x plus 4. And then I evaluate this, simplifying it all as far down as I can. So I'm going to have to square my binomial, distribute the negative 3, and then combine all my like terms. So that ends up being 25x squared plus 40x plus 16 minus 15x minus 12 plus 1. I ran out of room. Let me erase the line. So minus 12 plus 1. So this first part comes from squaring that binomial. The second part comes from distributing the minus 3 to each of these terms, and then I still have the plus 1 on the end. Now I can combine like terms. So I end up having 25x squared. So I have plus 40x minus 15x. So that's going to be plus 25x. And then I have plus 16 minus 12 plus 1. 16 minus 12 is 4. 4 plus 1 is 5. Now, if this question had asked me to find f of g of 3, I could take this 3 value and now substitute it in for all of these x's here. Or I could substitute in the 3 up here, solve for what you get here, and then put whatever you get from solving 5 times 3 plus 4. So what, 15 plus 4, 19. Substitute in 19 as your x value in the function of f. So you could do it 2 ways. So just keep that in mind. Be adaptable. Know that you could evaluate it multiple ways. All right, if I were to do the same thing for g of f of x, remember I like to write mine as g of f of x. My g of x is equal to 5 times x plus 4. This case, my x is f of x. I need a whole lot more room, because I have to fill a trinomial in there, fit a trinomial in there. So this is going to be 5 times x squared minus 3x plus 1. So I'm substituting my f of x value from here into the x's in my g of x. So to simplify this one, though, this one's a lot nicer because I just have to distribute the 5 within those parentheses and then combine like terms. So I get 5x squared minus 15x plus 5 plus 4. The only thing that combines are my constants, so I'm left with 5x squared minus 15x plus 9. And that is my g of f of x. Notice I do not get the same answers. When I compose this one, f of g of x, I got this trinomial. And when I composed g of f of x, we got this trinomial. They're not the same. So please be careful in the order in which you're composing definitely matters. This little next green section is just a reminder that the opposite or inverse function of square rooting something is to square it. So the square root of 9 squared is equal to 9. The square root of x plus 3 squared is equal to x plus 3. Remember, the square root of x squared plus 4 cannot be simplified. People want to say that it's x plus 2. It is not, because if you think about it, x plus 2 squared does not give you x squared plus 4. X plus 2 squared gives you x squared plus 4x plus 4. So you're missing a middle term. So that's not simplified by getting x plus 2. So just keep that in mind. We're going to evaluate and compose these functions. So remember, we're going to do f of g of x. So my f of x in this case is 5x squared minus 1. And my x in this problem is equal to my g of x. So that's going to be square root of 5x plus 5. But now I have a square root being squared, so that cancels the square root out, leaving us with 5 times 5x plus 5 minus 1. When we distribute the 5 on the outside to both terms in the inside, we get 25x plus 25 minus 1. So that's 25x plus 24, because 25 minus 1 is 24. So that is my composing of f of g of x. If I do the opposite and do g of f of x, my g of x is equal to 5 times x plus 5. My x in this case is the f of x, so it's going to be 5x squared minus 1. So small. Okay. So then here, I have to distribute the 5 to both terms inside here. So that gives me the square root of 25x squared minus 5 plus 5. Here, minus 5 plus 5 is equal to 0. So that just gives me, those cancel out, and that gives me square root of 25x squared. These are not combined with addition, and since both of them have a perfect square, this perfect square of 25, the perfect square root of 25 is 5. The perfect square root of x squared is x. And so this simplifies down to 5x. So this is my g of f of x, and this is my f of g of x. And again, notice how I did not get the same result. Whew. I'm going to go over a few more examples because I know that this is kind of an interesting concept that you might not have seen before, and so I wanted you to see a lot of different examples. So here we have given f of x equals 3 divided by x minus 4 and g of x equals 2x minus 8. We're going to find f of g of 9, and then we're going to find g of f of 6. So I'm going to show the first one one way and the second one a different way. And so you can kind of pick which way you like. So let's do f of g of 9. The way I'm going to do this is I'm actually going to find g of 9 first. So up here, I'm going to do some work to find g of 9. G of 9 will equal, I just take my function g of x and replace the x's with a 9. So 2 times 9 minus 8. 2 times 9 is 18, minus 8 is 10. So what this means is that what I'm actually finding is f of 10. Because I found out what is g of 9 equal to. It's equal to 10. So I substitute 10 into my function f and then evaluate. So this is 3 over 10 minus 4. That's going to be 3 over 6, which simplifies down to 1/2. So f of g of 9 is equal to 1/2. Okay? The other way I'm going to do differently, I'm actually going to find g of f of x and then substitute in the 6 afterwards. So g of f of x, that's going to be 2 times 3 over x minus 4 minus 8. I'm going to multiply this out. So remember the 2 is the same thing as 2 over 1, which will give me the numerators multiplied together. 2 times 3 is 6. And then 1 times x minus 4 is still x minus 4. And then minus 8 at the end. So this is my g of f of x. So now to do g of f of 6, I just substitute in 6 into this function. So I get 6 over 6 minus 4 minus 8. So that's going to be 6 over 2 minus 8. And then we get, so 6 divided by 2 is 3. 3 minus 8, I get negative 5. So what I would recommend is if you're asked to do one individual problem with the same, like with two functions, I like to do it this first way. But if you are going to have to evaluate, let's say we had to do g of f of 6 and g of f of 10 and g of f of negative 1. Like evaluating the same functions with the same, like with these different numbers, I would probably do this way because I get a general result and then substitute each x value into the general result. But if I'm only having to find one, I might do it this way on the left-hand side, just because of personal preference. I'm going to recommend that you try 17 and 18 on your own. I'm going to say you should pause. I'm going to solve it and just show you the result. But then this has an added part to it where you're also finding the domain of f of g of x as well. So go ahead and try these on your own and then come back and check your answers. Okay, so I have the answer to number 17 here with my work kind of shown. You can see that your denominator, the minus 2 and the plus 2 would cancel, and so therefore you're just left with 3x, or 3 over 3x, which simplifies down to 1 over x because 3 over 3 is just 1. So I have 1 divided by x. X cannot be equal to 0 because it's in the denominator, and so therefore we have the domain negative infinity to 0, union with 0 to infinity. The reason why I came back before you did 18 is because this one's actually asking you for two functions of f and g that would give you h when you compose them together. So I like to do this in the easiest possible way. I like to say, okay, what would be like my parent function? And so my parent function for here would be like a square root of x. Okay, that's like the normal parent function for a square root function. But I don't want my x to be just an x. I want my x to be this 3x minus 7. So what I do is I then make my g of x equal to the 3x minus 7. And so what two functions, when I compose them together, would give me this? This is one example. F of x equals the square root of x, and g of x equals 3x minus 7. Because when you compose f of g, your g of x becomes your x value in here, and that will give you h. Okay, h of x. So that's one way to do it. Some people like to do it a different way. There's not necessarily one right answer for this. Another pair that could work for this would be if you had f of x equals x minus 7, and your g of x equaled 3x, because your x here will be replaced by the 3x, and that would also give you h of x. And so just so you know that there are more than one possible ways to come up with combinations of functions that when you compose them together, you can get a different function or the same function. All right, let's try another one like this. We have h of x equals x plus 1 cubed plus 8. We're told to find two functions f and g such that h of x equals f of g of x. So two functions that I can compose together to get h of x. Again, I'm going to look at my parent function, but in this case, I might want to say, what if my parent function isn't just my regular parent function? What if it's x cubed plus 8? Okay, because I have that plus 8 added on to this kind of chunked together cubic. So if I have my f of x is equal to x to the third plus 8, then my g of x would need to be what I want this x to become, which would be x plus 1. So this is one possible combination for functions that when composed f of g of x, you would get the same thing as h of x. Another pair that would work for this is what if I had f of x is equal to x plus 8 and g of x is equal to x plus 1 cubed. When you compose those together, you would also get h of x. So again, there are two possible combinations and maybe even more. You could keep looking for more that could get you the same h of x when composed together. The last part of the algebra of functions is going to be actually evaluating the subtraction of functions, the addition of functions, etc., at certain values from the actual graph. And so what we're going to do here, we have two graphs. We have f of x, which is in blue, and we have g of x, which is in red. And what we're going to do is we're going to evaluate the subtraction of them at each of these, or subtraction or division or composition at each of these values of x. So the first one is f minus g of 3. So what I'm going to do is I'm going to come to 1, 2, 3 on the x, and I'm going to look at, okay, what is my f value? My f value is 4. My g value is 3. And so I'm going to subtract them, and I get 1. For the next one, we're evaluating g divided by f of negative 2. So I'm going to go on my graph. I'm going to go to negative 2. My g of negative 2 is negative 4. My f of negative 2 is positive 2. And so negative 4 divided by positive 2 gives me negative 2. All right. The next one is when we're composing. We're going to do g of f of 1. So what we first do, or again, remember, I like to write it as g of f of 1. So what I first have to find is f of 1. Let's do this in green. F of 1 is equal to 2. So this is the same thing as saying g of 2, because f of 1 is equal to 2, based on looking at the graph. So then I now need to evaluate g of 2. So I look at where x is equal to 2, and I look at what is my g value. My g value is equal to 4. So that's how I compose functions from graphs. I look at the first, like the inside function, evaluate that at the certain x value, then I substitute the evaluation of that function into the other function. All right, I'm going to do one more before my time runs out. F of g of negative 3. So first I'm going to find g of negative 3, and that equals negative 4. So this is the same thing as saying f of negative 4. So then I go to negative 4, where x is negative 4, and I look at what my f value is, and that is negative 2. So this evaluates at negative 2. All right, 8 seconds left, so I'm going to go over the last one, just the answer. I'm doing f of negative 3, and you get your answer as 2.